Welcome to Airpaw. Airpaw, AERPAW, stands for Aerial Experimentation and Research Platform for Advanced Wireless. Located primarily on and around the grounds of North Carolina State University in Raleigh, North Carolina, USA, Airpaw is a national wireless research facility. It is funded by the U.S. National Science Foundation under the Platforms for Advanced Wireless Research, or POWER program, and is one of 4 power platforms funded by NSF under this program. The development and build of the power platforms is overseen by the Power Project Office, funded by the NSF for this purpose. Each power platform focuses on enabling cutting-edge research in advanced wireless topics and focuses on various challenging directions. Airpaw focuses on enabling experimentation at the intersection of advanced wireless technology and unmanned aerial vehicles, or drone technology. The project to design and build Airpaw started in September 2019. Within months, the COVID-19 pandemic brought the project nearly to a grinding halt for several months. However, the project team persevered, found ways to make progress, and Airpaw started to come together, until finally, after almost 2 years of work, the Airpaw platform first opened to use by researchers with a small set of core capabilities. In November 2021, we held a hybrid workshop with hands-on tutorials and in-field demos for in-person attendees to introduce Airpaw to the wireless research community, followed by the announcement of general availability of the platform. Since then, Airpaw has been continuously adding both experimental resources as well as features and capabilities. The added resources and capabilities are planned to become generally available for use by experimenters in the latter half of 2023. Now let's take a closer look into Airpaw capabilities. Airpaw is intended to enable experimentation in support of a broad range of wireless research topics, from waveform design and antenna characterization to wireless networking and advanced wireless application design. Especially the confluence of advanced wireless and drone topics, where wireless networks serve drones, but drones also may serve wireless networks, such as network slicing, increasingly small and variable cell size, side haul, 3D aerial networking, disaster recovery networks, represent research topics that Airpaw aspires to enable. For this, Airpaw uses software-defined radios and a custom vehicle and vehicle control platform fabricated from off-the-shelf hardware, open-source code, and purpose-built Airpaw software. Thus, the researcher using Airpaw for experimentation has access to programmable radios and programmable drones, which they can fully program themselves. At the same time, Airpaw provides its users with access to some industry-standard real-world commercial equipment such as Keysight RF sensors, or a complete small Ericsson cellular system with base station and core network. These equipment were received as part of the in-kind contributions of the Airpaw grant. Rather than use them simply to enable Airpaw internal operations, Airpaw aspires to enable a national community of researchers access to experimentation with these equipment. Not only are they real-world equipment, they are installed not in the artificial environment of labs, but in real-world conditions, at various places in a 1,500-acre research farm and the urban environment of the Centennial campus of the NC State University. Operation of such wireless equipment and aerial autonomous vehicles are subject to regulations from the Federal Communications Commission and the Federal Aviation Authority, respectively. As valuable as the experimental equipment, Airpaw is in possession of the appropriate licenses and exemptions required to operate all this equipment. Full details of the Innovation Zone license granted to Airpaw the specific experimental licenses as well as the FAA exemptions are available from the Airpaw website and user manual. This, however, poses a practical dilemma for a research facility that aspires to allow unfettered, deep access to such equipment. Airpaw's value comes from its physical characteristics, but to be of practical use to the nationwide community of researchers, it has to be remotely accessible. Thus, access to Airpaw is heavily mediated by computers and the Internet, but Airpaw is not fundamentally a computing facility. The inclusion of commercial equipment not designed for such delegated use makes things more complex. The modality that Airpaw adopts in order to balance these limitations is one adopted by many physical research facilities, from telescopes and microscopes to wet labs, that of batch execution. To enable researchers to have as realistic an experience as possible, the Airpaw team has built a virtual environment that is accessible through a programming environment indistinguishable from that of the physical environment of Airpaw, and whose radio frequency and airspace characteristics are close digital twins of the physical environment. As the Airpaw user manual points out, this feature of Airpaw also allows researchers to access Airpaw without worrying about possibly violating FCC or FAA regulations. This burden is taken over by Airpaw itself. A web-based portal allows an Airpaw user to log on from anywhere on the public internet. An experiment can be initiated in Airpaw's virtual environment entirely through the web portal. The experimenter accesses Airpaw's virtual environment by standard secure shell or SSH sessions that allow them to view the source code for sample experiments provided by Airpaw and build on them to create their own custom experiments. The experimenter can use the virtual environment to run emulated sessions of their experiment at intermediate stages of development and see visualizations of the execution. When development is complete, the experimenter can submit the experiment for testbed execution. Airpaw's platform control and orchestration framework, consisting of a large amount of custom automation as well as human operators, move the exact code developed by the experimenter in a containerized fashion to testbed nodes and trigger testbed execution. During testbed execution, overseer containers as well as human safety operators monitor the radio and vehicle usage by the experimenter's program and abort the experiment in case of impending unsafe or non-compliant operation. Thus, the experimenter never leaves the comfort of their own office or lab, need not have a pilot's license, nor worry about the consequence of unintentionally violating FCC or FAA regulations. At the successful conclusion of the testbed execution, the experiment is returned to the virtual environment, so the experimenter can again log in and seamlessly view the results gathered by their experiment. The Airpaw website and the user manual linked from it guide the researcher every step of the way. A researcher can learn to use Airpaw entirely by using the self-paced tutorials provided by Airpaw, together with walkthrough videos, and successfully perform experiments on Airpaw without ever visiting Airpaw in person.
Okay, so this is a video about creating a project under Airpaw, and it is assuming that you either created a project from the previous video, or you were added to a private project, or you joined a public project. So you have a project that you are working with. And let me go back to, this is the project we created in the previous video.
This experiment is going to cover sample experiment SE1 LTE SISO using SRS-RAN. For this video, we're going to focus on just the radio and traffic portions and save the vehicle portion for a second part. Here we have two terminals which represent a fixed node and a portable node. The First step we're going to do is we're going to navigate to the folder containing all of the radio scripts.
Other modes of Airpaw use, involving more direct access or more manual operations, are possible. Although the canonical self-programmed access methodology we just described makes most efficient use of resources and automation and is the cheapest to use. Let's have a look at all that Airpaw offers again. Airpaw's wireless resources are deployed over a small area of NC State's Centennial campus and largely over the Lake Wheeler Agricultural Field Laboratory, also owned and operated by NC State. They consist of highly programmable generic wireless nodes, both fixed and portable, comprising commodity workstation computers and software-defined radios, as well as industry-standard specialized equipment. Airpaw also provides programmable autonomous vehicles, both air and ground, including a helikite for long-term experiments. The footprint of the deployment area has increased significantly with Airpaw's Phase 2 deployment. Many more interesting experiments involving multiple nodes and larger spans are possible in Phase 2. Airpaw's custom-developed vehicles and software libraries, together with the digital twin of the Airpaw physical environment, makes highly repeatable mobility experiments possible in Airpaw. Because the vehicle trajectories are programmatically determined, running the same experiment multiple times ensures that the drones follow precisely the same trajectories each time. Since the same program can also control the software-defined radios, joint vehicular autonomy and wireless experiments are easy to develop in Airpaw. Airpaw's combination of features positions it as a unique resource for researchers to study and invent the future of wireless-powered, uncrewed aerial vehicles. Since its original Phase 1 opening in 2021, Airpaw has been continually used for active research, not only by the Airpaw team itself, but external users around the country and even international collaborators. Some have focused on issues lower down the stack near the physical layer, while others have focused on network protocols and characterizations. The Airpaw helikite has been deployed to collect long-range data not only in the Lake Wheeler area, but also the highly crowded Raleigh downtown area. We have published a number of papers with our findings enabled by Airpaw, and so have others. A recent search showed more than 100 published papers that referred to Airpaw. All the wireless data collected by Airpaw is made publicly available through the Airpaw website. In May 2023, we held our second Airpaw Community Workshop, attended by more than 100 participants from 39 distinct universities and a few industry representatives. Over 60 participants went through hands-on tutorials, starting from registering as an Airpaw user and ending with running several sample experiments in Airpaw's virtual environment. They attended demos, as well as some actual executions of Airpaw experiments in the field.
COVID didn't help any, like everybody else in the world, so it was kind of a challenge. But we're excited to have them out flying again and doing the right things, and here to help anytime you want, and I hope to see every one of you back here running.
For the second or third policy. So now if I do start experiment at SH here, and then do screen -ls, so you see the transmitter has started. So I go to the EVM M1, and then we can also check the
Many of them went away, professing an intention to use Airpaw for their research, and many have actually started doing so since. We hope this introduction to Airpaw was useful for you, and that you, like them, might find use in Airpaw.